estimate here. So we're trying to estimate the population variance using the sample variance, right? That's what we take samples for. But when we plug an estimate into an estimate, things get a little cloudy. And the way we adapt for that is we punish ourselves a little bit. We punish this variance measure by dividing by n minus 1 instead of n. Right? You already told me divided by n minus 1 makes it bigger. Basically, dividing by n minus 1 is our way, or statisticians' way of being honest with themselves. That, hey, we plugged an estimate into an estimate. We've got to admit that really clouds the results a little bit. And I think I probably have it on here, so I'll show it to you just to make you feel bad, because it's like a page of math. I'll actually show you exactly why it's n minus 1. Well, why not n minus 2? Wouldn't that punish us? Yeah, that would punish us. Why not n minus a half? That would punish us. Why n minus 1? For those of you that really want to know, I've got a slide on here for you. But you don't need to worry about that if you don't want to. You can trust that n minus 1 is the right amount. By the way, we will do things where that becomes n minus 2, n minus 3. But believe it or not, every damn one of you is gonna, oops, it's Sunday morning. Every damn one of you is gonna understand why it's n minus 1, why it would be n minus 2, why it'd be n minus 3. It all has to do with putting estimates within estimates. And truthfully accounting for that. In fact, forget all this crap for a second. There's a famous quote. There are lies, there are damn lies, and there are statistics. Very famous quote. Anybody know who said that? Disraeli. Who said Disraeli? Excellent, Kevin. Big brain on that guy, huh? Benjamin Disraeli, who actually, if I don't do this, I will get bored with the class, so I go off on tangents. Anybody remember the band Cream? They had an album called Disraeli Gears, which was kind of a mixture of a bike term and Benjamin Disraeli. So if you go play trivia and you get that question, you owe me part of your winnings. All right. Yeah, it was Benjamin Disraeli. And what he meant is, you can lie to me. You can really lie to me. But the best way to lie to me is just to manipulate your statistics. Basically, it's saying, you can do anything you want to make statistics tell you what you want, and then you're not just lying to me, but you're pretending like you have the support of the data, which is far worse. Okay? So, to start with, everything I teach you in here will be under the assumption that we are doing it legitimately, not to deceive, and to do it the right way. So when I say we need to admit that we plugged an estimate into an estimate and, in a sense, punish ourselves by inflating that a little bit to adjust, what I'm saying is, if we want to be honest about it, that's what we do. Okay? Along the way, though, I'm going to show you the way people will, Sunday mornings really cramp my style, BS you by taking that. You give me a data set, I can tell you anything I wanted to tell you. Let's not have to go, that's not right. Sooner or later, it would probably catch up with me, ruin any consulting I do, that type of stuff. You'd be surprised how many people do that. Fairly sickening. But I'm going to assume you're all moral, ethical people who are out to do this the right way. That does not mean that you shouldn't be able to detect when someone else is doing it. In fact, that might be one of the more useful skills that pops out of this, is not so that you can manipulate the data, but so that you can detect it better when someone else has. There are little tells, like when, well, we'll get into it. I don't want to get too far ahead. But that's certainly one way we're going to approach this. I have to say, I've sat in a few seminars or presentations where and I admit I'm a bad person, I say this gleefully, I absolutely destroyed people who did that. You brought me a real good feeling. Kind of like, I caught you, and now I'm going to show it to everybody in the room. Because I just an opinion, but I take great offense to people that try to pull that stuff. All right, so that's sample variance, sample standard deviation, and it's something we're going to use a lot, so you need to know how it's defined. But really, it's just the square root of the variance, which is easy, because it means the bigger the variance is, the bigger your standard deviation is going to be, because it's just the square root of variance. So there's not a lot to know about standard deviation, square root of variance, and bigger means more spread out. Yeah.
I hate standard deviation.
You hate it?
Yes. Try to explain to me for the 18th time in my life what that means.
Standard deviation.
Yes. I mean, I understand. I can look at the graph.
All right. So for now, and we're going to talk about a lot. For now, just to start getting there, what is variance? Rocky, put it in your words.
Yeah, it's the distance from the average, basically.
More or less, kind of punished by squaring it. But that's too complicated. I don't want to get complicated. Variance is simply a measure of how spread out the data are. Right? Do we all agree with that? Mm-hmm. Now, there's more formal definitions about how to calculate it. I don't care. That's not going to help us intuitively. Variance is how spread out the data are. And in a lot of senses, the more spread out it is, the less precise your predictions are going to be. If everything was kind of right around one number, you know something around there is going to be a pretty good prediction too. If everything's spread out, it's like, well, what do we do? Yeah, we can calculate kind of the median or the average. But is that good a prediction? Well, it wouldn't have predicted these things on the end very well. So, variance, cool? Okay, so standard deviation is just the square root of variance. So it too is just a measure of how spread out things are. That's what I want you for now. I'm not giving you a wave of the hand answer, we're done. But for now, all standard deviation is it's an alternative. It's tied to variance, but an alternative definition of how spread out data is. Okay, and in fact, let me just take a pause here, and we'll get into something that kind of leads to the next part of standard deviation. It's not going to be conclusive yet. We gotta fill in the little parts before I show you formally. But I think you're gonna like this. So you all come to me, I'm your real estate agent. You say, how much is this house gonna sell for? And I say, well, $100,000. But is that what people really usually say?
No.
What I think they usually say, and I mean, that's what the fact some of you are already doing it means, okay, most people know this, is that $100,000, give or take $5,000, right? There's a give or take, right? I'm not saying everybody does that, but that's a pretty common thing. That's their way of conveying to you that I am not saying it's going to be exactly 100,000, but I'm pretty confident it's going to be between 95 and 105.
Or it's going to deviate between $50 and $100.
Something like that. Yep, something like that. Now, let me give you another statement. It's going to sell for $100,000, give or take $90,000. You laugh, but it's because you already have a deep understanding of standard deviation. Okay? Because what we're working towards is we're not just working towards kind of saying 100,000, give or take 5,000, give or take 90,000. In fact, statistics is going to show us exactly what the give or take is. So our estimate is going to be our estimate, the 100 grand. But depending on how spread out our data is, what the sample variance is, what the sample standard deviation is, that's going to say how much of a cushion we need in our prediction. And it works like this, and we're getting a little ahead, but that's okay, because I like to set things up early and return to it once it's already kind of percolating. let's say I want to be 90% sure that when I say it's between these two values, like 95,000, 105,000, though, let's say I want to be 90% sure that that the real price ends up being between those. My data actually tells me what values will make that happen. So, we don't know how to do that yet. But if we look and we calculate the sample mean, the sample variance, those type of things, the estimate we get will tell us what to predict. And our standard deviation will help us say, and how far do we need to make that interval, if you will, of values that we expect, that we think are okay, that might happen. Now,